In the previous lectures, I tried to introduce materials, their significance, and the journal information, most of that was given to you. Then we moved towards classification of materials, and there were a number of perspective aspects on the basis of which materials are divided into different groups. Then, if the students remember, we reached a point that materials, the atoms in materials can be either in a proper periodic arrangement or they can be randomly oriented and placed randomly throughout the volume of the material. So that divided the materials into two groups: crystalline materials and non-crystalline materials, or amorphous materials. So now we are taking from there that amorphous materials are also very, very important, and a large number of materials with enormous applications are among the amorphous materials. For example, glasses, most of the glasses where there are more than and then you have many individual compositions within the glasses. Then when the amorphous structure is there, then we make amorphous alloys, which are metallic glasses, and they have enormous applications. But in our course, the focus is on crystalline materials. So why crystalline materials in the first place? Because crystallization or crystallography give us a map of the material. The map of the material means the arrangement of atoms in a material. Why do we need that arrangement? If they are perfectly arranged, each atom at its proper place, then there will be little chance of the moment through. They are perfect ionic solids, for example, and there are no free electrons there. So electrons are chance of anything. Electricity, for example, they don't conduct. Heat is done by the metals. No, don't conduct. It will be heated up, but the conduction of heat will be much slower than that of metals or other materials. So the arrangement of atoms in a material tells you about the properties of the material. And I have discussed in very much detail that from where do the properties arise, the origin of property. So the origin of property is in the atomic arrangement. If you know about the atomic arrangement of a material, then you can predict the properties. If you are expert in the atomic arrangement of material, then you can arrange these atoms artificially and engineer or tailor the material according to your application. You can convert an insulator into a semiconductor, a semiconductor into an insulator, a semiconductor into a good conductor. So you can engineer your material according to your need. So you tailor the property. And how do you tailor the property? By changing the arrangement of atom in the material. Electromagnetic properties, mechanical properties. Electromagnetic properties are associated with the electronic cloud. That if that electronic cloud is, I will say that when the center of mass and the center of charge are coinciding, you will have a spherical atom, and a spherical atom will have no polarization. So by changing that spherical nature, you can polarize the atom. And when you polarize the atom, you polarize the material. And that polarized atom will give one type of material and non-polarized type of atom will give a different type of material. So you can dope the material with certain elements, atoms, cations, which changes the electromagnetic behavior of the material. Similarly, if atoms are arranged in full order, so a little bit disturbance will take that disorder throughout the material. For example, you are cracking something and the material has no obstacle in the middle. So when you start cracking a piece of wood or something, the crack will go up to the end without being interrupted. So the mechanical properties of that material will be much poor if you introduce certain obstacles to the propagation of crack. The same thing is true for materials, that you can change the mechanical properties of material via doping, via playing with the symmetry of the material. And so the electromagnetic and the mechanical properties and other properties up to electronic properties, other advanced properties which are used in modern world. So crystallography is basically giving you the expertise to know about the distribution of atom in a material, and the distribution of atom in turn tells you about the properties of the material. Defects and doping, they are born by crystallography, because you are creating such defects which introduce a specific type of property, but you suppress one property and enhance the other property by introducing materials of your choice. It's just like food, that if you like a saltish taste, so you increase the salt in the material. If you don't like it, you decrease that. So it is a sort of doping, you can call it. That, for example, you need more polarization, then you will put such atoms in the material which can be easily polarized, which can change the electromagnetic behavior of the material. Similarly, you can create defects for anionic conduction, for electronic conduction, for various sorts of conductions. You can change. On the left hand side, just next to this text, you see diamond and graphite. Diamond is 100% carbon, graphite is 100% carbon. But if you look into the structure, this is crystallography. That in diamond, all the bonds are strong bonds. And diamond is used to cut steel. It is such a hard material because of the crystal structure. And on the bottom, you see the graphite structure, in which the layers are bonded as strong as in the case of diamond, but interlayer bonding is much weaker. It is some sort of physical bonding, and that is why the graphite is one of the softest material, and people use the graphite pencil for writing. So it scratches even on paper, but on diamond, it cuts the steel, but it destroys the properties according to your desire. So crystallography is one of the properties. Now, what is crystallography? Let us go to the very basics, fundamental things. As I have told you in the start, that the Callister material book is basically followed at this level. So use the Callister. The focus of a teacher is use anywhere. But specifically, when I'm in front of you, my job is to motivate, tell you, or the papers can be learned from there. But let me tell you what the book and the other things are not telling you. So first of all, when you take a topic, when you select a topic, your job is to first look into the significance of that topic, that why is it needed. If it is not needed, then why in the first place you are studying it? So the aim of the teacher is to tell you the outcomes of your study. If your study doesn't have outcomes, you don't have any aims, then why waste time on crystallography and all these things? Crystallography is a very artistic subject. It is difficult in the start, but once you learn it, you will enjoy it. So crystallography is a branch of science that examines crystal crystals, a complete subject. It as a topic, but it is a complete subject and it is a huge field. Crystals may be small, for example, virus are big, like big quartz crystals. The word crystal came from the ancient Greek. Crystallos are phonetically cross tal las is equal to cold plus drop. Cold is always associated with water or ice, and drop means solidity. The what you can say conciseness, limiting the space, solidifying type thing. It was basically quartz, which mean both ice and rock. Ice means softness, crystallinity, and rock means solidness, toughness, hardness. So when it is hard and proper order, you will know the details because specific shapes, you look around in your mountains, in your earth, in land, and when you see a specific shape or a specific geometry, it attracts you. The colors are coming because of the interference of light with material. So the different colors come because of the different type of diffraction occurring inside a crystal. So the geometry and the shape and the colors, they always attracted the human eyes, and they used to be used as ornaments, medicines, even in 4500 BC. So when we look into the calculation, it's about 6500 old history they are referring to, that people like them. The law of constancy of angles, that each face of the crystal will be a fixed angle, was established by Stinson in 1638 to 86. He lived during that period. And J.B. Lewis Rome D. Isle, 1736 to 1790. Then Hoy gave the concept that crystals were made by the orders taking up identical building blocks or bricks or whatever you call them, but he was the person who first gave the concept of the unit cell. So keep in your mind, don't lose the sequence. First, people liked them. They didn't know what they are 100 years ago. So the millions years old mankind didn't know about the crystals for 400 years. When it is people started to know things. Then Hoy, in 1822, he died and born in 43, gave the concept that crystal were blocks, which people now call unit cell, but he was the first who said that. During the 19th century, mathematical concept of symmetry, just like a parallelepiped, a sphere is more symmetrical than an elliptical shape. So keep things simple to not lose the concept of what you are studying. So they give the mathematical concept of symmetry, governing the repetition of motifs around a point or the repetition of patterns by translation, give rise to the concept like point groups, group of symmetry elements, symmetry axes, mirror planes, etc., passing through the center of a body. If you remember in the previous lectures, I clearly told you that the decisive factor between an amorphous and a crystalline material is translational symmetry. Imagination of the observer, the environment doesn't change. This means from where the observer started and where the observer reached, that is called translational in a proper manner. Then you 50 years later, using the limitation of previous letters and the limitation, I basically probably inappropriate word, the rules and the regulation imposed by the 14 brevis lattice and the whole crystal structures, all the crystal structures are divided into these uh, 230 space groups. But as I told you, despite these breakthroughs, they couldn't help molecules and what positions do atoms occupy in a crystal. Is whatever they were available at that time, they couldn't resolve the crystal planes even. Uh, the atoms and the molecules are much smaller than that. So because optical microscopy are visible as a quartz crystal, but they didn't know about the science inside them. And it took years to recognize X-rays as of medical interest and of interest in material science to know about the crystal structure. And Nobel Prize was given important discovery.